Hello everyone and welcome on today's video. My name is Wouter Pere and I'm the founder and main developer of GHEtool Cloud. And I'm very happy with the subject of today's video because we succeeded in improving the accuracy of our geothermal simulations quite a lot. And this we did by allowing, by default from now onwards, varying fluid properties. Now, why this matter and why our geothermal designs can only benefit from this improvement in GHEtool, we will discuss in this video. Let's start by a small recap of the borehole thermal resistance. Now, if you have not watched our video on this topic, please do so, it's linked in the description below. But what we know is the effective borehole thermal resistance describes how easy the fluid can exchange energy with the ground. And we said it consisted of a couple of resistances. The resistance from the fluid to the pipe, through the pipe, and then through the ground to our ground. And this is the borehole effective thermal resistance. And since this resistance tells us how easy it is to exchange energy from the fluid to the ground, it also has a big impact on the fluid's peak temperatures and hence our design. Since the larger this borehole thermal resistance is, the higher our peak temperatures will be and the more borehole meters we need in order to be able to stay within the temperature limits of our simulation. So this is an important parameter, and we said before that this borehole effective thermal resistance, it depends heavily on the Reynolds number. Now, if we do a small recap of the Reynolds number, we said that the Reynolds number is on the x-axis below and the effective borehole thermal resistance is on the y-axis. And as you can see, the borehole effective thermal resistance varies quite a lot, especially in this region around 2300. We discussed that region before, and we also talked about the accuracy between Earth Energy Designer and GHEtool. But this region is what's called a transition region. So if we jump back into what the Reynolds number basically was, is it tells us something on how the fluid behaves. So if we have a low Reynolds number, we have what's called a laminar flow, and the fluid is well behaved, and all the fluid particles, they move parallel to each other. For a very high Reynolds number, we have a turbulent flow, and this is very good for heat transfer because since all the particles are tumbling over each other, it's very easy to give away the heat or exchange the energy with our borehole and with our ground. So this is typically the region you want for your system, although it has a higher pressure drop and hence also a higher pump consumption. If you're not familiar with pressure drop, there is also a video in the description below if you want to know more. And then there is in between this transition zone where the borehole thermal resistance drops with respect to the laminar flow and it transitions towards the turbulent flow. Now this Reynolds number, which determines where this transition zone starts and ends, it's described as follows. So it takes into account the speed of the fluid inside the pipe, which depends on your flow rate, of course. But then we have here the density of the fluid, we have the viscosity of the fluid, and these are properties of the fluid itself. And this is the last step before we can actually dive into the innovation, which is saying that the fluid properties, and these are two for monopropylene glycol, 20 and 30%. The lines differ from different antifreezes, but the story is the same. As you can see, the higher the temperature, the higher Reynolds number you will get, due to the fact that your viscosity will decrease, your density will decrease a little bit as well. And when you go below the freezing temperature, your antifreeze actually starts to work against the freezing of the water, and your Reynolds number drops significantly after that. And it also depends on the level of antifreeze you have. Typically monopropylene glycol is rather viscous, so it has a lower Reynolds number. Now what's important to know on this figure is that when you have around 0 degrees Celsius for a particular pipe, it does not really matter. We have a Reynolds number of around 1000, but when we have, with the same fluids, we have a temperature of 15 degrees, it's over 2000. So when you think about your geothermal bore field and your temperatures that typically fluctuate between the 0 and the 20 degrees, there's actually quite a lot of difference in Reynolds number. And if you then recall our previous slides, where depending on where the Reynolds number is, you have quite a different effective borehole thermal resistance. This is actually a very important aspect which is it's often neglected. So historically, let's say every simulation was done with one effective borehole thermal resistance. So what we did was we took the temperature, the minimum average fluid temperature, which you put in as a threshold for your design. We took that temperature, we calculated all the fluid dynamic properties, we calculated the Reynolds number, and then we found the borehole thermal resistance. And that's the way it's been done for decades. It's a very robust, very safe way, which historically was quite enough because most of the demands was just for heating. So it was all extraction. So this approach actually makes sense. The thing is that the temperature we have when we inject heat into the ground, when we're cooling, is actually quite different from the temperature we get when we're extracting the heat from the ground. And hence we also expect that the borehole resistance will be different in injection and extraction. And that's actually the improvement we made with this newest update of GHEtool. What we did is we calculate now by default. You can disable it, and we will go over that in just a second, with varying fluid properties. Now, why is this important for you? It is important because we will now calculate way more accurately how your fluid behaves into the ground, and especially for injection and cooling with these higher temperatures, which also have a higher Reynolds number and hence a better borehole thermal resistance. Another main advantage of this improvement is that we are less sensitive to gradient errors. Now, if you recall our discussion on that, due to the fact that when you use GHEtool to calculate the required depth, when you're drilling deeper, the ground heats up and it becomes harder to cool your building or to inject the heat into the ground. And this can cause gradient errors. Now, with this improvement, since this higher temperature also improves the borehole effective thermal resistance, there are way more suitable solutions when you use this method. And thirdly, due to the fact that we're now more accurately calculating the borehole thermal resistance, we will end up with more feasible systems in the end. And geothermal energy will become way more, let's say, way more attractive as a solution. So it's really interesting, a really interesting innovation. Now, I suggest we jump into GHEtool Cloud. I'll show you around how this works, what different results you can expect, also when you can't expect a difference in results, and then we will wrap this up. So here we are in GHEtool Cloud. I created a new project, and let's just dive into it. I have a minimum temperature of 0 degrees and a maximum temperature of 17 degrees. My ground properties are just the default values. My bore field, I took 5 boreholes in the width direction, so we have a line with 5 boreholes of 100 meters borehole length. For the resistance, which will be important, we took a double U-tube in this case, with quite a good thermal conductivity of the grout, DN32. And for our fluid, we took 30% monopropylene glycol and a flow rate of 0.3 liters per second. And as you can see, this gives us a laminar flow through our system with a borehole resistance of 0.14. If we go back, let's just show also the thermal demand. It's just the default values, so nothing to see there. The general tab now has this extra option, temperature dependent fluid properties. Now by default this will be yes, meaning that you will be automatically calculating with the more accurate simulation methods. Now I will just put it to no for this first simulation, and this will basically mimic the behavior you've used to with GHEtool, also with Earth Energy Designer and with other software. So let's go ahead and calculate it now. And what it will do, it will take the 0 degrees we set as a minimum temperature, and we calculate the resistance, and we have 0.143, and this is the temperature profile we in the end up with. Now this is the result we're used to. Let's now go ahead, duplicate this, and use the newer, more accurate methods. Therefore, we just say, yes, I want to use temperature dependent fluid properties. I press calculate again. It can happen that this takes slightly longer, but you will barely notice it. And here you now see that we have two effective borehole thermal resistance, one for extraction, one for injection, and also two Reynolds numbers. But the temperatures are almost the same. We have 17.24 here, 0.27, and also in minimum, it's more or less the same. And this is due to the fact that both Reynolds numbers are now still laminar. So we are not in that very good regime of the turbulent flow. Now what is interesting is that this effective borehole thermal resistance in extraction, this 0.1427, is somewhat better than this 14.3. And this is because our temperature in peak only goes to 3 degrees, which is not a 0. So it's not by definition that by using this more accurate method, you will always see a giant leap in performance. In this case, since we're using a double U-tube and we're both laminar, there is not quite a lot to see here. Now let's change our design. Let's go to scenario 3. And basically I will rename it so it's easier to jump around afterwards. I know it, call it single U. Let's go back to the borehole resistance step. And now let's say we have a single U-tube. And here you can see that the borehole resistance is actually very, very bad because we're in a single U-tube now, less area to transfer the heat. And this is the final result. So what we can see in the extraction rates at the laminar, we have this high borehole thermal resistance of 0.22 or even 0.23 actually. But in injection, we actually have a way better borehole effective thermal resistance. We even have a turbulent flow. And this is because we are in 17 degrees in this case. So our fluid is way less viscous and it flows way better. So this is actually quite a big difference. And just to compare it, what you would have had previously, if we go make it scenario 4, go back to the general tab, set this accuracy measure to no, and now we will calculate how we used to calculate it. And here we have used the same worst case effective borehole thermal resistance, and here you can see we're actually crossing the limits. We're going to 19 degrees. So previously, if you had this design, you would have said, well, okay, I need an extra borehole in order to cope with this cooling demand. But now to this improvement in accuracy, we see that for the same 500 meters of borehole length, we actually stay under the 17 degrees because of borehole resistance is actually better. And this has another major advantage, because if you want to calculate the required depth, you've been used to getting the gradient error, probably. So just call this required depth. I will calculate the required depth as we used to do. Now I will say, let's drill 4 boreholes and see what this gets us. So let's calculate it. And what you now will see is that you will end up with a gradient error. Due to the high borehole thermal resistance, we cannot inject the heat into the ground. We need to drill too deep. This makes the bore field too warm, and we cannot solve this problem. So the solution here was actually drill another borehole in order to find a solution for this problem. Now, if we use temperature-dependent fluid properties, what you'll actually see is that we will calculate with a better borehole resistance for this injection, for this cooling, and hence we will not quite as often, it still can occur, but quite as often, we will now end up with actually a solution to our problem. As you can see here, so with 155 meters, we're actually able to heat and cool our building with a geothermal system due to the fact that our effective borehole thermal resistance is better with these high temperatures. So this was basically the story I wanted to tell you. It's just basically the beginning of a couple of improvements we have planned for later this year. I hope you found this interesting. I hope you will all start calculating with this temperature-dependent fluid properties. It's embedded in all the versions of GHEtool Cloud because we want you to design the best systems as possible, and we want to enable you by providing you with the methods and the models for that. If you have questions, please reach out. If you have ideas for other articles of methods, please let us know, share this video, subscribe, follow us on LinkedIn, try GHEtool out, and I hope I can see you for the next breakthrough in the next video. Take care.